Good morning, everyone. My name is Nikta Sarkar. I am the CFD application engineer here at KETIV Technologies, and I welcome all of you to today's Ansys Virtual Academy session. Today, we're going to be talking about how to do underhood thermal management using Ansys Fluent. And I'm very excited for this session because I'm going to be talking about some tips and tricks that we very frequently use, even if we're not necessarily doing underhood thermal management. So hopefully all of you have some good takeaways from this session. So for today's agenda, we are going to be discussing some Ansys CFD capabilities for getting the most fast and accurate analysis results for underhood underbody flow. You will see that there are a lot of simplifications that are available within the Ansys Fluent framework that you can use to cut back on the setup time and also get the most fidelity and accuracy for your solution. And it doesn't always have to deal with thermal analysis. Sometimes engineers are just interested in modeling the flow through the engine bay or the underbody domain, just to see if there are any recirculation zones. So we're going to be talking about the cold flow analysis as well. And as is common with any CFD application, there are some pre-processing, solving, and post-processing steps involved. So we'll talk a little bit about the geometry cleanup and the meshing part, and then what sort of simplifications can be used within Ansys Fluent to make our setup easier, less time consuming. And then for the post-processing part, I'll talk about some of the flow variables that I am interested in the demonstration that I will do. And that might provoke some questions from you guys about, hey, if I want to see this, how do I go about doing that? As always, if you have any questions, please feel free to leave them in the Q&A box that you see on your screens. And if you have any comments about the AVA or suggestions on how we can make these better, you can always participate in the post-AVA survey that is launched. Thank you as always, and I'll go ahead and get started. So before I delve into the how-to of the presentation, I wanted to talk about the why. Why am I doing this AVA? And if you've never done underhood thermal analysis or underbody analysis, why would this AVA be of interest to you? So whenever we are talking about, vehicles, there's a trade-off between aerodynamics and thermal management, right? You need to select a cooling package for your machine that will provide sufficient cooling to ensure that the heat that is being transferred from the energy sources, say, for example, the engine, doesn't overheat the components around the heat source. If the components get overheated, depending on their proximity to the heat source or perhaps the material that is being used, that can lead to, damage over time, or in extreme cases, even failure modes. So that is why it's very important to make sure that your flow and thermal analysis is performed accurately when you're dealing with vehicles. And this is where Ansys can, provide you those extra capabilities that will make it easier for you to analyze so many different parts and assemblies without taking up too much time or compromising on the fidelity and the accuracy of the solution, right? And even on the pre-processing stage, Ansys has a lot of tools, especially nowadays with the more recent releases, wherein you can work with complex dirty geometry and easily use wrapper-based meshing technology to prepare your domain for the CFD simulation, right? And then in cases like these, you have cooling packages themselves. It is not efficient to be able to actually model the geometry of those cooling packages. So there are some simplifications that you can implement within the Ansys Fluent framework. And these concepts of perhaps using an empirical model or lumped model to replicate the realistic flow parameters it is not just relevant to this particular application, but you could use the same concepts for many different CFD applications. And I will talk about those as and when we get to that particular part of the presentation. So on the pre-processing side, I briefly want to touch on this part. I want to focus more on what we can do within Fluent itself. But when we're working with vehicles, there are a lot of parts and assemblies. And unlike, cases in which you are looking for, component level analysis, perhaps you don't need to spend so much time in retaining features that will not really add any extra accuracy to your simulation, or perhaps that level of accuracy is not required when you're doing an external flow on this scale. So keep those parameters in mind when you are cleaning up your geometry, because perhaps you can get away with a dirty geometry instead of retaining all the features and making sure that everything is connected. When I say that, you can get away with a dirty geometry, what I mean is, unlike in other cases wherein we have a watertight geometry and we're able to extract a closed flow domain out of this sort of a geometry, we can work with wrapper-based meshing, wherein you have almost like a plastic bubble wrap that will wrap around your dirty geometry, and that'll be your basis for the surface mesh. So in those sort of situations, you don't really need to make sure that your holes are plugged, your geometries are not touching, and you don't have to spend that extra amount of time to retain like individual features that do not contribute much to the overall flow analysis deliverables, right? So Fluent itself has two extremely capable guided meshing technologies. We've already done AVAs in the past. If you're curious, please make sure to check them out. What I would be using for this sort of an analysis would be the fault tolerant meshing workflow, which again wraps your mesh around the dirty CAD geometry. So these are some points that I briefly wanted to touch upon in case somebody's getting started with Ansys Fluent, but will mostly spend time in today's AVA within the solver itself and talking about the steps that are frequently used to set this sort of a problem up. So for today's AVA, what I thought I'll do is I'll do a demonstration, but I will talk about the different steps taken in that demonstration side by side. And in doing so, I hope I will be able to explain to you what are the steps or what are the considerations that you have to keep in mind while setting this up within Fluent. So for an example case, I've taken a very simple geometry, which again is a dirty geometry, as you can see from the screen, wherein you have a radiator cooling core in front of a fan, and then you have an engine chassis. Now, this is the bare minimum, bare bones, sort of a vehicle body analysis. In real world cases, you'll have a lot more components, a lot more parts. But for the sake of, like saving time and saving setup steps, I have just, chosen a very simple example. What you can see here is the radiator, the shroud, the fan, and the engine assembly. And what we have available to us is the heat exchanger performance data through the radiator. So we have flow rates for air, which is passing through the radiator, and then the coolant as well. And then we also have the air side restriction, which will help us set this radiator up in a more simplified form instead of actually modeling it, right? And then you have this entire assembly situated inside a tunnel in which only one face, this front face, is open to the atmosphere. Everything else is a wall. So this is an extreme sort of a case. Think of examples in which your machines are working in mines, wherein you don't really have open, atmospheric conditions in all directions. So if this is an extreme case like that, it becomes all the more important for you to keep in mind that your cooling package is able to provide sufficient cooling, right? In this particular case, we just have the radiator, but in an actual cooling package, you might also have the condenser, you may have the oil cooler, but the concepts and the steps that you would take to set them up would be very similar. So that's what I'm going to be showing in today's demonstration. So what you see on the screen right now is the heat exchanger performance data that we have available to us already, right? So you have some coolant flow rates in the horizontal direction, and then you have your air flow rates in the vertical direction over here. And in this table over here, you have the air side restriction. This is usually available when you are trying to select a cooling package for your particular machine. So this is also very important, and I'll talk about this in just a second, right? So before we do anything, before we even go to Fluent, the first thing as a gut check that we would do is to make sure that the effectiveness that you're getting from these different rates is less than 1. Why? Because if your heat exchanger effectiveness is more than 1, that's not realistically possible because you're able to transfer more heat than is available to you as an input, right? So you can easily easily calculate the effectiveness for all these different flow rates, both from the coolant flow rate and the air flow rate, using this calculation over here. So you have your coolant, which is your auxiliary fluid, and air, which is your primary fluid, and you can calculate, the effectiveness by taking the C minimum, which is your heat capacity, by multiplying the specific heat into your flow rate, right? And when you calculate this effectiveness, and I have only done this for one data point, you could do that for all the data points to ensure that it is less than 1, you will notice that you're getting 0.8291. So this particular data set corresponds to this cell over here. So one can repeat this for all these cells over here. If it comes out to be more than 1, that would be a problem in Fluent itself. So when you try to set this up, Fluent will give you an error, which is why this gut check is important, right? Now, when we are setting up this model within Fluent during the demonstration, I will tell you how we are using this data to simplify setting up the radiator instead of actually modeling the geometry or the complex nitty-gritties of the geometry in Fluent. Now, the other thing that we have to keep in mind is that as air is passing through this radiator, and there is a primary direction in which air is passing, we have to model the cooling core as a pressure restriction zone. Why? Because this radiator has a complex geometry, your air flow is going to experience a pressure drop at a certain velocity. So instead of actually modeling the geometry, we can use something called the porous media formulation, in which it is very simple for you to just specify some resistance coefficients that will essentially mimic the same effect of having a restriction, geometrically speaking, in the flow. Now, by omitting the step of modeling the geometry, what are you doing? You are basically saving yourself time, setup time, and also solve time, because your mesh is not that fine. Now your mesh can be a uniform, simple hexahedral mesh without having to, keep into mind, the fins or the geometry that would be expected from a heat exchanger like this. So how does Fluent do that? Fluent does that using this particular expression over here, in which D and C are your different coefficients. The term that has viscosity is the viscous coefficient, and then you have the density term, which becomes your inertial coefficient. If you are able to calculate the value of D and C in this equation, and you plug that into Fluent, which I will show you when I'm setting up the case, then you will be able to essentially tell Fluent that, hey, my air is passing through this zone. Please provide this much pressure restriction for this amount of flow rate, right? So remember I told you that this table over here is important. So this table is the table that we will be using to calculate D and C. So this table gives you the pressure drop for a certain velocity. For engineers, this is very easy to obtain from suppliers. Suppliers will usually give that to you. So this is a common, DP versus V curve that we often see. Once you have this curve, you can simply plot this in Excel and get a trend line for it. And by doing this, what you're basically trying to do is find, find an analogous equation that looks like this equation over here. So if you notice, and if we rearrange the terms, you have, an x squared term over here, which refers to this term over here that deals with the inertial coefficient. And then you have a simple x term over here, which will give you the viscous coefficient. So by doing this sort of, a comparison of different terms, you can easily find D and C over here. So what I basically did was I took this term and equated it to this coefficient over here, 4.3631. And then I took this term over here and then equated it to 12.638. Okay. And we know the values of viscosity and density for air. So we have that available to us. And then delta X is basically the CFD thickness of the zone that you're going to assign. So for example, if your zone is, 5 millimeters in the direction of the flow, then delta X becomes 5 millimeters. So this is the thickness of the zone that you assign in your CFD setup. So because we have all these values available to us, we can easily calculate the viscous and the inertial coefficients. So when I do the demonstration part, you will see how we can plug this in Fluent. The other part, very important part, not just for Underhood thermal analysis, but a lot of different CFD analysis is fan modeling, right? Even when you're doing HVAC simulations for buildings, or if you're doing any sort of moving part simulation, how to set this up can be very useful to you, right? So the most intuitive way of doing this would be to have an actually rotating part, and then the mesh moves accordingly as the fan keeps moving, based on the speed that you specify, right? But remember, when the mesh is actually moving within Fluent, that becomes a transient analysis. You need to, select a smaller time step, and it becomes computationally very expensive, right? So how can we simplify this sort of a realistic, setup? What simplification does Fluent have to offer to replicate the same effect without making it so time consuming? So for today's demonstration, I'm going to be showing you how to set up the moving reference frame model or the multiple reference frame model. But then there are other models as well that I just want to briefly touch upon so that you have this knowledge at the back of your head. So what is the MRF approach, or the multiple reference frame approach? This is also called the frozen rotor approach, in which you're not actually moving any solid parts, but what you do is you assign relative velocity to a particular zone. And by assigning that relative velocity to that particular zone, you're essentially telling the Fluent software that, hey, this zone is actually moving, but because my relative velocities can be assigned as such, all I'm doing is converting a transient problem to a quasi-steady problem, and then getting the variables from there instead of actually moving the mesh. So this simplification allows you to do a steady state analysis without having to, write any codes for moving the mesh, or without even using a sliding mesh for doing the same problem. You basically create a separate mesh, a separate zone that encompasses all your moving parts. So for example, if you have fans and impellers, you can create a zone around these moving parts and specify that as a moving reference frame zone, and assign the velocities as such to get the same effect. Now, when you're setting this zone up, It can be both conformal or non-conformal, and you can take care of that when you import the mesh inside Fluent, because keep in mind that when you're dealing with underhood, underbody simulations, you'll usually be using tetrahedral elements, right? And because the mesh is so complicated, because the geometries are so complicated, there might be times when your zones are not conformal, meaning the mesh points do not align. So in those cases, interfaces are automatically created when you import that into Fluent. If not, you can do that manually as well, right? The other thing to keep in mind is that there are some limitations with using the moving reference frame approach. One factor to keep in mind for sure is that depending on how you set up the moving reference frame and how much area is encompassed within that zone, you may expect recirculation, which may or may not be accurate. So it makes sense for us to, keep the moving reference frame or design the moving reference frame zone as such, so that you don't get these non-physical recirculation zones, which you perhaps wouldn't get if you were to do an actual moving mesh in the simulation. So here you have an example of a moving reference frame zone. If you can make out, you have the fan blades within this particular zone. And this is very similar to the example that I'm going to be showing in the demonstration today. What you basically do is you define a zone, then you find the rotation axis origin, then you define the rotation axis direction, and then you specify a velocity. So very simple for a basic case like this, in which you have a simple rotating solid body, okay? It becomes a little bit more complicated when you have other interfering stationary walls as well. And again, there are some limitations on which cases you can use the MRF setup and which cases you can't. For example, in this slide over here, you can see a rough outline of the engine body. Then you have the fan, and then you have a heat exchanger over here. And this green line over here depicts the shroud of the fan, right? Now, when you're setting up a moving reference zone for this particular fan, how do you determine the extent of the zone, right? Because this you have to set up in the pre-processing stage. You have to create a separate volumetric domain for this part over here. So how do you determine, hey, how big or how small does this have to be? So a good recommendation is to make sure that it is as big as possible. And in this case, I would make it extend it to touch the shroud. Why? Because if it is any less in height, I mean, by height, I mean, if it doesn't touch the extent of the shroud, then you have a small zone over here where you'll get high recirculation. So you want to avoid those sort of, inaccuracies. So which is why the most accurate way of setting up a moving reference frame zone is to make sure that it encompasses as much area as possible, especially if there's a shroud around, then you make sure that it touches the cylindrical portion of the shroud as well, right? And then from an actual extent point of view, make sure that, the domain extends between the engine and the fan, and also between the heat exchanger and the fan blade, as you can see over here. Now, when I said that, there are some restrictions to the moving reference frame setup, I also want you guys to keep in mind certain guidelines for these particular zones. By default, all the walls inside the moving zones are stationary. What I mean is in Fluent, when you specify stationary or moving wall, you can select whether it's an absolute formulation or a relative formulation. So inside the zone, since the fan is actually moving, this is stationary respect to the zone itself. Because remember, we have specified a velocity to the zone. So what I'm basically telling Fluent is that this solid body is rotating in an absolute reference frame. So by default, stationary velocity relative to the adjacent cell zone, which is the moving reference frame zone, would be 0, right? If it is not rotating, for example, in the case of the shroud is not rotating, only the blades are rotating, right? If this shroud falls within the moving reference frame zone, then we need to make sure that the absolute velocity of that non-rotating wall is specified to be 0. So if it is a stationary wall, then you have to declare it stationary in the absolute reference frame. And when I do the demonstration, this part would be a little bit more clear. The last thing to keep in mind as a restriction is that the stationary walls that are inside or touching the moving reference frame zone, they need to be axisymmetric. You cannot have a random object inside the moving reference frame zone that would have different relative velocities compared to the fan blade when it is actually moving. Because if you do that, then you cannot transfer that sort of a movement to a quasi-steady approach. So whatever stationary walls you have inside your moving reference frame zone or touching the moving reference frame zone, they need to be axisymmetric, or they need to be a surface of revolution, so that the relative velocity between any point on the moving blade and that stationary zone is always the same. If it is not always the same, then it cannot be a steady problem, right? And then you'll have to do it the standard way, the transient way in which the mesh is moving. And then, you have other approximations as well, apart from moving reference frame. For example, the sliding mesh approach, wherein you actually specify a zone that is sliding with respect to another zone. And this sort of a approach can be very simple to set up as well, provided that you have axisymmetric, conditions, provided you have surface of revolutions. If you have random solid stationary walls within your fluid zones, then there might be an issue using this particular approach. The other thing is using a lumped parameter fan model. In the lumped parameter fan model, you are basically specifying a boundary condition at one particular fan plane within a fan zone. And it's almost like specifying a pressure restriction curve, similar to what we did for the porous media case. This is a very simplified way of setting up a fan model. But if you have a lot of fans in your domain, for example, you're doing an entire building analysis and you have 30-40 fans, then for those situations, this sort of a fan model works well, because you're basically specifying a momentum source and you're specifying a pressure restriction, and that gives you the same sort of effect as modeling an actual fan. The other thing that I wanted to cover, which is not part of the demonstration today, but usually when you're doing underhood, underbody simulations, this sort of a geometry might pop up, wherein you're working with grills or screens. Again, with the grills or screens, you can see that the actual pores or actual holes are very small. To be able to capture them as it is, you would have to ensure that your mesh is really fine. And that's just unnecessary solve time that you don't need to add to your overall simulation. So again, what you can do is you can use a porous jump formulation. This is similar to the porous media formulation, the only difference being that the porous jump is a single boundary and not a volumetric domain, whereas the porous media is an actual volumetric domain, right? So you have same sort of coefficients that you would calculate from the pressure restriction curve. You would have a thickness to this porous medium, even though this is a boundary in your CFD setup, but in your actual physical grill, you would have a thickness along the direction of the flow, and then you can calculate the phase permeability and the pressure jump coefficient from your pressure restriction curve and assign that as a simplified phase, right? So again, you save a lot of time by not actually having to mesh the grill. And then, you have conjugate heat transfer. This always comes in handy whenever you're doing a thermal analysis. I know that I've talked about this in the past, the advantages of having shell conduction available within the Fluent framework, wherein you don't actually have to model the thickness of the solid body, but just having, this option of specifying certain layers and thickness in your wall boundary can mimic the planar and normal conductivity just as you would if you were to actually mesh the wall and have some cells in the solid thickness layer. So with that, let me just, start with the demonstration, because I think I'm kind of running out of time. So I'll go ahead and explain some of this while I'm doing the demonstration itself. I'll go ahead and share my Fluent screen. Please let me know if you guys cannot see it. Just give me 1 second. So you guys should be able to see my Fluent screen right now. So let me know in the chat and Q&A if you can't. But until someone tells me, I'm going to assume that I'm sharing my screen correctly. Okay. So what I have over here is the same problem statement that I described earlier. I have a radiator over here and a fan over here. Let me show you. The geometry better. So you have your fan blades over here. You have your radiator over here. I have made it slightly transparent so that it is a little bit more clear. And then you have a random engine chassis over here. Now this entire assembly is encompassed within a tunnel. So if I were to show you everything, you'll see that this has basically walls on all its sides, and then this front face is open to the atmosphere at 0 gauge, right? So when I start setting up the simulation, the first thing that I do is I input my mesh and then I look at my scale, okay, to make sure that my domain extent is selected correctly. Now, you would do this for any CFD simulation for sure, but why it becomes very important in any situation, especially in this, is because remember, you are going to be specifying your fan rotation axis origin, right? So what units you are using for your length are very important, because I have seen cases in the past wherein, you specify a certain rotation axis origin, and then the units are completely off, and then the fan flow looks completely absurd. So keep in mind the units that you select for length, temperature, and anything for that matter of fact. You can always look at the units over here and change the units as you deem fit. For this sort of an external flow analysis, the pressure-based solver works well. And I'm going to be using a steady state analysis over here because, we're just going to be looking at, the flow and thermal heat transfer in the radiation. But as such, we are not looking at any transient characteristics. Keep in mind, though, in the industry, there are a lot of cases wherein you would have to do a transient analysis. For example, a hot shutdown case wherein your machine is shut down abruptly, and then it starts, cooling down in a transient fashion. So for all that sort of analysis, transient analysis might be necessary. This one is just simple for analyzing flow. So we're going with a steady state analysis. Energy equation is on. And for turbulence, you can use a realizable K epsilon model. That works well for external flows like this. You will also notice that the mesh that I'm using is mostly tetrahedral, except for in the radiator zone. Why? Because when we are modeling the radiator, we are going to be using the porous media formulation, and it is recommended that for any sort of porous media formulation, you use hexahedral cells. So if I were to show you the porous radiator zone, you will notice that, this is a lot more structured, and this gives you a little bit more accuracy in terms of straightening the flow, because when the air is passing through this radiator zone, it's going to be straightened out. And so we want to mimic that accurately, which is why we go with more hexahedral cells if possible, right? For fluid properties, and this is important, you can use incompressible ideal gas. Incompressible ideal gas basically means that your density is not changing so much because of pressure, but it might change because of the temperature, right? And when you're working with high heat sources such as the engine, this is something that you might want to consider, right? And then you can vary the thermal conductivity and viscosity with temperature as well, in case you have the data points. For example, here, I had 4 different data sets. So, I basically entered the values at different temperatures. And what Fluent does is it gives you a graph of the points that you've entered so that you can compare it with any curve that you have on your end and see if you've entered this correctly. And it also helps you understand how the values are changing with temperature. So if you see an absurd curve, then probably your data is incorrect, or maybe you entered something incorrectly. So this is a cool feature as well. And then if I were to talk about the moving reference frame zone, which is something that I have been talking about. So this basically encompasses all the moving parts for this particular problem, right? And you will notice that it doesn't have any stationary parts as such. So everything that is inside this zone is actually moving. The fan blades are actually moving. So you can go to cell zone conditions, click on this zone over here, and you will see that I have selected frame motion. So this is what you do in order to specify a particular zone as an MRF zone, okay? And then you specify the rotation axis origin and the speed of your fan. And the other thing that you have to keep in mind is your rotation axis direction. Now, this is very important as well, because if your direction is reverse, then your flow goes in the other direction and your simulation is completely wrong, right? So use the right-hand thumb rule, use the angle of attack of the blades to make sure that you're specifying the correct direction of the fan flow, so that your flow gets pulled in the right direction. Now, because all the moving parts are within this moving reference frame zone, and it is not really touching any shroud, or it is not really touching any stationary part, I don't have to actually go into the walls and specify anything. So for example, if I were to go to my moving reference frame zone and look at adjacent boundaries, you will notice that everything is interior. So even though it says wall, it's actually a part of my interior boundary condition. So you can see over here, it's interior. And these guys over here, if I were to display this, then this is the fan wall itself, which is actually moving. So if I look these up in the boundary conditions, you will notice that, not this one, let me see, blade, yeah. You will notice that this has been assigned as a stationary wall. But stationary with respect to what? Stationary with respect to the adjacent cell zone. And my adjacent cell zone is a moving reference frame zone. That means this guy is moving, right? So this is what I wanted to highlight earlier about the difference between actually stationary and actually non-stationary objects that touch or are included within the zone. If it were an actually stationary zone, then you would actually select moving wall and then select an absolute value of 0. Because when you select an absolute value of 0, you're saying, no, this is completely stationary in my domain. This is not moving with respect to anything. But for this case, let me not change the settings here, and we'll keep this as it is. Now, the other thing that I wanted to talk about is the radiator. So let me go ahead and display this guy over here. So there are no fins. There is nothing in this radiator. It's just a simple, cuboidal domain, right? So how am I simplifying my radiator like this, right? That's where Fluent comes in. If you select this guy over here, you will notice that, okay, somebody asked a question as what is considered as a positive rotation direction? Positive rotation direction in the sense, so for example, sorry, let me just backtrack a little bit and I'll show this guy over here. For example, in this case, depending on the angle of attack, I can tell that my blades are, going to turn like this. So what I'm going to do is I'm going to use my right hand thumb rule and make sure that my hand curls the way it would if I were to, use my right hand thumb. And that would indicate that the fan axis rotation is in the positive Z direction. So when I go to my MRF, you will notice that the rotation axis direction has been specified as Z is equal to 1. If it were the other way, if it were the other direction, then I would put -1. So hopefully that answers the question. Okay. So coming back to my radiator zone, sorry. The first thing that we do is we make sure that this is assigned as a porous zone. Why? Because this is not just, an internal zone without any restriction. As the air passes through it, it is going to be restricted because of the actual presence of fins and other geometries, right? The heat exchanger solid body, which we are not actually modeling. So how do we do that? I already talked about calculating the inertial and viscous coefficients. This is where you define them. And the first thing that you do is define the direction of flow. In this case, the direction of flow is in the -Z direction, right? So if I were to turn on the fan, you can see that my flow is moving in this direction, which is in the opposite direction of positive Z. So when I specify this porous zone, the direction 1 vector is the primary direction of flow. So this part is important. So I'll specify -1, and then it automatically calculates the direction 2 vector, which is going to be perpendicular to direction 1. You can also use the plane tool to specify these directions. So you could basically create a plane on this surface over here. And then when you click on update from plane tool, Fluent will automatically get the vectors for you. But in this case, it was simple to put it down manually. So I went ahead and did that. So this flow is moving in this direction. So Z is going to be -1. Okay. Now this direction 1 vector is very important. Why? Because in this direction, you are going to be specifying the actual coefficients that you calculated. So remember in my presentation, I calculated the value of D and C. So this is where I'm entering it. So C is entered here and D is being entered here. Now, what am I specifying in direction 2 and 3? Now, keep in mind, I'm assuming that all the flow is moving in the minus C direction. I am not really expecting any trans flow in the X and Y directions. So if you're not expecting any flow in the other directions, simply add a couple of zeros to make sure that the resistance in those directions is so high that the flow cannot travel in the X and Y direction. So whatever value you get for D and C, just multiply that with 1,000 or multiply that with 100 and make sure that those are the coefficients mentioned in the other two directions. So this way you are ensuring that flow is only going to move in direction 1 vector. It's not going to travel in direction 2 and direction 3 vectors. And I'm noticing that you guys have some questions, so I'm going to get to that in just a bit once I finish the setup part of the simulation. All right. The other thing that we did for this particular simulation is specify a heat exchanger model. Now, this radiator is a heat exchanger, and we have the heat exchanger performance data, right? How can we use this data to simplify the heat exchanger specific inputs that we provide for this particular zone? So you have a couple of ways to do that. I have chosen the ungrouped macro model for this particular demonstration. Now, heat exchanger models is, it can be a separate topic of an AVA in itself. So I'm not going to delve too much into the depths of it. But basically what you do is you divide the heat exchanger zone into macros and tell Fluent the inlet and outlet temperatures of the inlet temperatures of the auxiliary and the primary fluid being the coolant that is entering the radiator, primary fluid being the air, okay? And then you can actually enter the heat transfer data that I showed you guys earlier over here. So as long as you have this information available to you and the flow rates available to you, you can go ahead and enter this data, right? So you will tell Fluent, how many auxiliary fluid flow rates you have and how many primary fluid flow rates you have, and accordingly it will build this table. Now, when you do this, Fluent is able to calculate the number of transfer units for the heat exchanger, and make sure that the heat rejection rate is accurate if you compare it with a hand calculation of the same heat exchanger. So Fluent is going to do all that for you in the background. All you need to do is to make sure that you provide Fluent with this data. And then Fluent is going to calculate, okay, depending on these flow rates and depending on this heat transfer rate, what is the effectiveness, how much heat is being rejected. And accordingly, from this heat exchanger report, you will be able to tell at the end of the simulation whether it was enough for the engine bay or for the underbody environment in terms of sufficient cooling, okay? So you could go ahead and enter the heat transfer data, you could enter the inlet temperatures, and then this part is important, wherein you tell Fluent how many rows are available per pass and how many columns are available per pass. So I'll show you one thing over here. So this is my zone over here, right? So you will notice that there are around 60 rows and 70 columns. So for one pass of the coolant, right? For one pass of the coolant, you have 60 rows per pass and 70 columns per pass. So this is what you are specifying in your heat transfer setup over here. So if you had more grid points, for example, instead of having 70 columns, you had 90 columns, then in the geometry part, you would define it accordingly. And this allows Fluent to divide this zone into these individual small little zones, wherein it is calculating the heat transfer accordingly. Again, it is going to ask you for the pass to pass direction, right? And so you tell them, like, in which direction is your auxiliary fluid moving. And again, you can do that from the update, from the plane tool. Depending on the zone on which you specify, for example, I have chosen the heat exchanger zone to be assigned to this particular fluid cell. This extent of the domain will be automatically calculated, so you don't have to do anything over here. The only thing that you have to tell them is how many rows are available per pass of the coolant and how many columns are available per pass of the coolant. And this is going to be dependent on the mesh that you choose. The next tab is the auxiliary fluid, wherein you basically specify the specific heat of the coolant itself and what is the flow rate and what is the inlet temperature. So just by doing this part over here, just by entering this simple data over here, you are essentially able to replicate the heat exchanger that you would be able to see in this radiator instead of actually modeling it. So after you do all this, you are ready to run the simulation. If there are any non-conformal meshes in your geometry, suppose you had a separate hexahedral mesh for your porous zone, but your surrounding zones are tetrahedral in nature, then you could go ahead and create an interface for them. In this case, for example, if I show you these two guys, you will notice that they're not exactly matching. So do you see that the node points are not matching? This is what I mean by a non-conformal mesh. So an interface had to be created in order to make sure that data from one mesh is able to be transferred to the other mesh, other adjacent mesh, right? So you can go ahead and do that as well. So after all this is done, I go ahead and run the simulation for a couple of iterations. It's not converged yet, but I wanted to show you what sort of data you can get from a simulation like this, right? Let me go ahead and show you this guy over here. So 3. So this is the velocity magnitude that you're getting in a vertical cut plane. And you will notice that the fan is over here and the porous zone is over here. And you can see how the velocity is propagating throughout this cut plane. You could also look at vectors as well. You could also look at path lines. These path lines can be forward or reverse in direction. So let me look at one thing. So if I were to go ahead and do that. So you will notice that these are the forward path lines from the radiator that I've selected. But some of the path lines get sucked back in, and this can be a cause of concern because if you are getting heated flow that is being sucked back into the radiator, then you're not going to be able to get as effective cooling as you want for cooling your engine bay. So that can be an issue as well. There could be other things that you take into account. For example, if you are looking at the temperature in the cut plane, you will be able to see that there's cold air that comes into the radiator, and as the air passes through the radiator and comes in contact with the coolant, or rather exchanges heat with the coolant, your air gets heated, and this is the air that then goes into your engine bay. And remember, the cooling package should be sufficient enough to provide sufficient cooling for the engine bay, right? So for example, if you had a separate heat source for your engine chassis, or through any other tubes or pipes, then that could be additional heat sources that would need to be cooled by this package over here. So this is not a convert solution, so take the solution with a grain of salt. But the idea is that depending on the flow velocities and vectors, you would be able to detect any issues with the cooling package that you have selected. You could also look at the heat exchanger report over here at the bottom. And what that does is it allows you to compute the heat rejection from the heat exchanger zone. So for example, after you run the simulation for a couple of iterations, you see that the total heat rejection rate by the radiator is 66 kilowatts. Now, depending on the amount of heat you are expecting from the engine bay or from the engine, you might compare this to that heat and say, oh, this is sufficient, or perhaps this is not sufficient, right? You have other values as well that you can get from the heat exchanger report. For example, outlet temperatures, inlet temperatures, mass flow rate. So all this is really important stuff when you're determining if your cooling package is designed correctly. The other thing that I wanted to show you guys is the flow uniformity on the radiator surface. So for example, if I go to the velocity magnitude, give me 1 second. Okay, let's see. For example, if you wanted to see, where's my mouse button? For example, if you wanted to see the velocity contours on the radiator in plane, right? If you look at the velocity contours on the radiator in plane, you will notice that the velocity is high in the region where the fan is situated. And then in the other areas, it's not that uniform. This is not good for a heat exchanger, because if you're getting this sort of a velocity magnitude contour and you're dividing the radiator zone into uniform number of cells, then the amount of heat exchange that you get from an individual macro will not be uniform everywhere. So this could be another indicator for you to rethink your cooling package design and perhaps, place the fan differently, or, work with the shroud design to make sure that you're getting a more uniform flow index on your radiator in plane, right? And then this is for the convert solution results, which I'm not able to show you in the Fluent over here, but you can see that in the radiator zone over here, because you've assigned it as a porous media zone, your flow is actually getting straightened. But as was visible with the path line, some of the flow gets sucked back in to the radiator zone, and that is causing extra recirculation, which is not desirable in this sort of an application. So those are, again, things that you can determine from this sort of a CFD simulation. So I hope that, all this was helpful in explaining how doing an underhood, underbody vehicle simulation and understanding the flow and thermal analysis may help you select a better cooling package or rethink your cooling package design. But if you guys have any questions, and I can see that I have some from YouTube as well. So let me go ahead and take them as quickly as possible. What is the constant heat source in Fluent? And how can we model heat transfer in Ansys Fluent? In case I get airflow less than target value to keep it thermal, how can I analyze what and where are the weak points of cooling package layout? Right. So that is what I was trying to illustrate over here, is that depending on your vector contours and your velocity magnitude, you can actually identify the regions in which your airflow is getting recirculated or your airflow is getting pulled back in. So you would need to, redesign your machine in such a way so that there isn't any scope for recirculation, or your flow cannot travel back and get sucked into the radiator inlet in this particular example. So a good way to do that is to look at cut plane velocities, cut plane vectors, streamlines, path lines, and also look at temperatures. For example, if I were to show you this guy over here, and this is in Fahrenheit, by the way, so don't get confused by the temperature scale. For example, you can see that the colder air is getting sucked in through the radiator, and then your temperature increases as such. But then there are certain regions over here wherein you see a very high temperature, and that is because your fan is not situated correctly, which I showed you in the velocity contour for the radiator in plane. So when the fan is not designed properly, or the shroud is not as such that you can get uniform velocity, then you will see higher temperatures in those regions. So depending on these metrics that you see in the contour planes, you can tell where the problem lies and how to fix it, right? So that could be another way to do it. As far as the other question about how to assign a heat source, you could go ahead and do that. Right now I don't have any solid zones as such, I only have fluid zones. But if you wanted to assign a heat source, say to an engine chassis wall, suppose you wanted to assign a heat flux, so you could go to the thermal boundary conditions and put a surface heat flux. If you have a solid zone, you could go ahead and assign a volumetric heat source. So for example, I could assign a heat source to any particular solid zone. It could be a constant, it could be an expression. This is by meter cube, so this is volumetric. I don't have any solid zones in this particular example, but if you wanted to go ahead and do that, you could do that completely. And similarly, for surface heat fluxes, you could use wall boundary conditions as well. So hopefully that answers those questions. Thank you so much. Those were very good questions. I just want to finish by talking about the next AVA, which is going to be held on June 8th. Keep in mind that we've changed the cadence of our AVAs, so we're doing one AVA per month. And the next AVA is going to be hosted by Graham Stevens, who is the newest addition to our Ansys application engineering team. We are very happy to have Graham here. He's going to be talking about increased electronics reliability via Ansys simulation. So a lot of good stuff will be discussed in that AVA as well. So please feel free to subscribe and join these AVA sessions, and hopefully we see you there next time. As always, if you guys have any comments or suggestions, please feel free to leave them in the survey after the AVA. So with that, I'll sign off, and hope you guys have a great day. Thank you so much.